Differentiation. All right. So it basically reverses the chain rule. Okay, here's a good example. The integral of tangent x, secant squared x, dx. Okay, you couldn't do this before, but now you can do this. Tangent x, secant squared x, integrating that. All right, the goal. The goal. We don't know how to integrate this using our basic rules, so we're going to rewrite this as the integral of f of u, that's f of u, please, f of u du. All right. So we're going to integrate a nicer function. All right, we want to integrate a nicer function. We don't know how to do that directly. Okay, by the way, don't just guess that. You have to show me the work here. All right, so here's the key. Let u equal, okay, one of the tricks here is I want you to be a guy whose derivative is also in there. Actually, there are a couple of good choices you can make. But give me an example of one guy who might be in there, whose derivative is also in there. Tangent x, right? Let u be tangent of x. All right. Although you could also let u be secant x. Turns out that works too, if you look at it. By the way, there are lots of trigonometries, right? So there are various paths you might take sometimes. But anyway, we're going to let u be tangent of x. All right. So you're going to write that. You should write u equals whatever on homework and on tests. That's part of your work. All right. Now, using the Leibniz notation, all right, that means that du dx, the derivative with respect to x, is what? What is his derivative? Secant squared x. Okay. But when we do a u sub technique, we normally write this in differential form. Du equals secant squared x dx. Now, once again, are we multiplying both sides by dx? Most instructors would say no, but it depends. You know, it depends if you're thinking in terms of differentials. Right? In any case, we normally write down the differential form. Du equals secant squared x dx. All right. So when we do all this, all right, so this integral here, I'll go ahead and rewrite it. The integral of tangent x, secant squared x dx. We're going to write this in terms of u and du. All right? Tangent of x is u. Look at this. What's du? It's all this stuff, right? So what does this become? It becomes the integral of u du. As a substitution technique, do you buy this? All right? All right? Okay? You agree we can integrate u with respect to u very easily. That's u to the first. How do you integrate it? U squared over 2 plus e. Never got that. Okay, you need to have your constant of integration there. Okay, u squared over 2 plus c. All right, we're not done yet because u is our creation. Okay, what should we do now? Well, yeah, substitute back. All right, what was u? It was tangent of x. So we have here basically tangent squared x over 2 plus c. All right, and that's going to be your answer. It's a family of antiderivatives. Any questions about that?
I do.
Okay.
I didn't understand what you said. You have to find something that's u that's in. I don't understand.
Okay, you want to find a u, and he's probably going to. He doesn't have to, but he's probably going to be in here somewhere, right? You want to find an expression who's probably in there, right? Whose derivative is also in there. That's part of the integrator.
Okay.
Well, he's a logical choice because this guy's his derivative, all right? Although secant x also would have worked, right? Because if secant x tangent x, that also would have worked, actually. Right. Sometimes you might have some choice, all right? Now, by the way, how can I check, if you have time at the end of the test, how can you check that?
Take the derivative.
Take the derivative, all right? You can differentiate to check. And lo and behold, if you take the derivative, right, this is 1/2, and then tangent of x all squared. 2 comes down, kills him. Tangent x all to the first, times tail, secant squared x. Basically, this corresponds to tail. All right? Corresponds to the tail. So this du guy, right, okay, is going to involve the tail here. So the u sub technique basically inverts the chain rule. Okay? It inverts the chain rule. Because when you're integrating, the tail's in there right now. And the idea is that you're trying to find out, well, whose derivative is this guy? The u sub technique helps us figure that out. Any other questions about this? Practice.
So you got let u equals tan x. Then how did you get d of u over d of x equals secant squared x?
This is Leibniz notation. Okay, this means the derivative of u with respect to x, right? I'm taking its derivative with
something that relates like that in one of these? Like you want to find?
Well, I mean,
What if
in
there's,
5.1 we go with some basic integrals, right? Here, you know the chain rule makes it more powerful, right? We could differentiate more things like sine of 3x, right? Okay. Well, now the use of technique makes us more powerful because we can integrate many more functions here. We can integrate many more guys here. Okay. Yeah, I know.
is this primarily for trigonometric?
No, trig, algebraic, no. Right? Yeah, the use of technique works anytime that you have, differentiability and all that stuff. Anything else? Practice, okay? You get good at this. Practice. It looks weird at first, but then, gotta keep practicing. Let's look at an algebraic one. It's a polynomial, in fact. Example. Okay, the integral of x squared, 4x cubed minus 5, all to the 10th dx. Okay, what do you think I'm going to... Now, by the way, if you're ambitious, you could do this using the old school methods. Just take the 10th power, using the binomial theorem, multiply by x squared, okay, integrate term by term. Maybe factor back. How do you feel about that? No. No. Let u be who? Who's a guy in here such that when you do the substitute... Okay, what do you think I'm going to use for u?
4x squared minus 5 to the 10th.
I want a guy who's... okay. In fact, you know what? I'm going to put the hints over here, all right? What do we want for u? Okay, we want a guy such that when we sub in, we'll make the integral nicer. Okay, a lot nicer, all right? We want someone whose derivative is also in there. Okay, its derivative, okay, is also, okay, in the integrand there, up to a constant multiple. If you're up by a constant, that's okay. We can adjust for that. Okay, up to a constant factor. Okay, those are easy to deal with. All right. Now, how can I make that integral look a lot nicer if I let u be what?
4x cubed minus 5.
4x cubed minus 5. 4x cubed minus 5. All right. Why? Because you agree that if I replace this with u, that's going to make it look a lot nicer, right? If I replace all of this. Because some of you might be saying, why not just x cubed? Well, then you're going to get 4u minus 5 all to the 10th. That's not that great, right? But if you make all this u, okay, that's going to make this thing look a lot nicer, all right? And then what's du going to be?
X squared times.
Well, what's the derivative here?
Just kidding.
What's the derivative? Well, x squared. Don't forget your dx, all right? dx is part of the differential form here, all right? Now, you might be saying, well, wait a minute, we don't have a 12 yet. That's okay. We can adjust for that, okay? You agree that the derivative here is basically a factor of the integrand up to a constant factor, all right? The 12 we can deal with, all right? All right? So this is the ideal choice for you, all right? Now, if you let u be x cubed or 4x cubed, that's not wrong, but then you're going to have to do another substitution, and you want to avoid a double substitution.
So the dx at the end is just letting us know that 12x squared is the derivative of u with respect to x.
Yes, that's what we're looking at. Yeah, that's right. Okay. The bottom line is x is the variable of integration. Okay, and you shouldn't be confused as far as that goes. Yeah, it won't be a problem. Now later on in calc 3, it'll be an issue because in calc 3, you're going to have dx, dy, dz, you're going to have double and triple integrals. Okay, so but here it won't be an issue. Yeah. 7, that's routine, right? Because remember, in chapter 7, we're going to discuss integrating 1 over x and 1 over u. All right, so these are common choices for u. A base, an exponent, a radicand, a denominator. That's not comprehensive, but, and an argument, in general, an argument. Okay? If you have, for example, sine of blah, 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 then we often let u be the blah, blah, blah. That's an argument. Okay. Basically, it's the inside guy. We like to let u be some sort of inside guy. That's kind of hard to reach or manipulate, such that if we replace that junk with u, we're happier. You agree that if I replace this junk in here with a u, I'd be a lot happier? See, that's the idea. All right. Any questions? Yeah, Paul.
You're saying not to mix u, your u and your x d
In the same integral. Meaning that you shouldn't write x and u in the same line.
So once you write like that integral sign, you should be mixing them.
You shouldn't be mixing letters. That's right. That's right. Not that that's necessarily horrible, but it's bad form. Because then you lose track of who's dependent on what and all that. Okay, so we have time for this. All right, and we're going to go back to 825, but all right, method 1. All right.
So in that case, what would you do with the 12? How would that fit?
Yeah, exactly. We're going to finish it. Okay, now there are 2 ways to finish this. Method 1 is the way that the students really like to do this. Okay, compensation. It makes more sense. Compensation. All right, and that's the standard way that I approach this. Okay, although I will briefly discuss method 2, though most people prefer method 1. All right. Method 1, compensation. This makes a lot of sense. All right, now this guy right here, this integral, I'm going to rewrite it. Okay, and folks, this is worth your time. Okay, if you do this step, I know it looks like a waste of time, but it's not a waste of time. Okay, you're more likely to get the right answer if you do it this way. Okay, leave a space here, leave a space there. All right, put x squared, copy the integram, x squared, 4x cubed minus 5, all to the 10th, dx. Now, here's what we're going to do. All right. Okay, what's missing in the integram? I'd really like to have a what? A 12. So you know what? Let's make it so. It's like completing the square, all right? I want a 12 there. But it would be wonderful if I could just change problems because I felt like it, right? Then your test would be very easy, right? I don't like this problem, I'll change it to something else. Here, I can put in the 12 if I pay for it. Now, if you're multiplying that integram by 12, what balances that? What compensates for that? Dividing by 12. Or multiplying by what fraction? 112. And you know what? We usually put it out here, okay? You don't have to, but it's usually convenient to put the 112, the compensator, out there.
Yeah. Why did you want the 12 there?
Because du had a 12 in it.
Okay.
And we're going to replace this stuff with the du. I need a du in there. All right. Now, warning. A constant is okay, okay? But you cannot have something like 1 over x. So don't try to pull a stunt where you put an x there and then 1 over x. You're not allowed to put the variable out here. That's the variable of integration. So you cannot put a 1 over x there. 1 over 12, that's fine. Okay. All right. So let's go on. All right. So then we get, okay, 112. Integral. All right. This stuff here. What does this become? U to the 10. We like that, right? That's a really, really nice integram. And what about all this other junk? 12x squared dx. Guess what that becomes? du. Right there, du. Do you all agree that's our new integral? And isn't that wonderful? Isn't that lovely, right? 1/12 integral u to the 10th du. We can do that very easily, can't we? All right? Let's do it. First of all, I'm going to unravel this. What should I put at the end? Plus c. That's good to remind yourself. Do it early, all right? We have 1/12. Okay, integrate u to the 10th. U to the 11 over 11. That's, okay, that's u to the 11th over, that's 132. Plus c, I'm one step away. What do I have to do?
Substitute.
Sub that. Yeah. U was whom? It was 4x cubed minus 5. I just raised it. 4x cubed minus 5. All to the, what's to the 11th now, right? Yeah. To the 11th over 132 plus c. You can differentiate this to check. Okay. Once again, notice that when you differentiate this guy, your tail is going to be 12x squared. Okay, so that du guy corresponds to your tail. All right. brute force, expanding it out. Questions? Questions? Yeah.
You said something was gonna turn into DU, is that 12x?
Okay, yeah. What was du? Yeah, I just erased that. What was du? It was 12x squared dx. We substitute 12x squared dx. That's just du now. Right. So if you have a u in here, you need a du over there, right? Remember, this is good form. You just want one letter in here. Okay, you can't have a mix. Don't mix up x and u.
So you wouldn't want like you wouldn't want like x to the 10th and du.
That's bad.
Or u to the 10th and dx.
I agree. Don't mix them. Right. That's exactly what I'm talking about. Again, it might not be inherently wrong, but it's really bad form, and that could lead you off on a bad path. Right. So yeah, you need to learn to match up. Right. Okay. You agree? There's a difference between du dx and dx dx, right? Yeah, big difference. Yeah. Very quickly, I'll show you the second method, and then in principle, if you feel good about this, you can finish the homework through 5-2. Although I will discuss more examples next time. All right. But let me show you the second method very quickly. All right. Well, I'll give you the idea. All right. Method 2. I call it Kill Bill. But it's the idea of solving for the thing that you want to kill off. So remember, here's the guy. Integral x squared 4x cubed minus 5 all to the 10th dx. All right. Remember, u is still 4x cubed minus 5. That's the best choice for u. Du is 12x squared dx. Okay, so it starts off the same as before. All right. Now, in the second method, what we do here is we know that this stuff here, okay, this stuff here is going to become u to the 10th. All right. The question is, what is the fate of all this stuff? What does x squared dx become? Well, look at this. You agree that I can solve for x squared dx. So you solve for the guy you're trying to replace. You solve for the guy you're trying to replace. That's Bill. You want to replace him. All right? Well, what do? I divide both sides by 12. All right? So then you get that x squared dx is 1/12 du. So basically what happens is you replace x squared dx with 1/12 du. Right? 1/12 du. All right? And that's another way you can do it. All right?
Where'd you get 112 du?
I'm sorry? I divided by 12. Divided by 12.
The whole du?
Sorry, what?
What are you dividing?
Du is 12x squared dx. I'm dividing both sides by 12. That means multiplying both sides by 1/12. Right? If you divide this by 12, you get x squared dx. Okay? If you divide by 12, that's the same thing as multiplying by 1/12. Okay? Now again, this is one reason why people tend not to like this as much. Okay? Although you could say that it might make more sense. Yeah, what do we replace this with? You might think that makes more sense. But then people have to think about what do we divide by and all that stuff. So people tend to prefer method 1. And I think people are generally a lot more comfortable with this first one. You can do it either way. Okay, but I think it's good to know both.